Here's another proof that I'd like to give you an example of. This is the second part of number 20. Let V and W be vector spaces with W1 a subspace of W. If T is a linear transformation from V to W, prove that the pre-image, all of the things in V such that T of X are in this subspace, is a subspace of V. So maybe start off with a little scratch work. I try to think about these things usually. So what do I have? I guess what I have is this set. I guess I have that W1 is a subspace. And then I want this set. I don't know, I'll call it A, X and V, such that T of X is in W1, subspace. And then, like, if you're saying, well, what does that actually mean? Usually when you have a subspace, what that means is zeros in it, X plus Y, additive closure, that's in it, and A times X is in it. And then probably to get this, what am I going to have to do to get this? I'm probably going to have to show those same three things. That's usually how you show a subspace. Okay, so with that in mind, let's prove this. Let's let A equal the set. I don't know if I'll need a name for it, but why not give it a name just in case? The pre-image here. Need to show A is a subspace of V. And it's just elements in V, so it's clearly a subset. First, I'd like to show that 0 is in there. T of 0 is in, well, it equals 0, right? So T of 0 in V equals 0 in W, which is in W1, since it's a subspace. So therefore, the 0 in V is in A. That's the first part of the subspace test. Second part of the subspace test, I've got to pick two elements in here, right? This is what I'm trying to show. So let X and Y be elements of A, meaning, right, what's it mean that they're elements of A? T of X and T of Y are elements of W1. By closure of W1, right? T of X plus T of Y. Funny thing about that, I'm just going to go through, I'm going to steal all of these, and I'm going to get them for the set that I'm concerned about. Is in W1. So, well, what is this? This is T of X plus Y is in W1. That's where we use linearity, right? Therefore, that's the very definition of X plus Y being in A. That was the definition of being in A. So we got that kind of closure. Now we'll do additive closure. Let X be in A and C be a scalar. We know Tx is in W1 by the closure under scaling. Well, you guessed it, C times Tx is in W. C of Tx equals Tcx, right? And so what were we trying to show? Tcx. So let's see, CX is in A, right? This is in W, so that's in W1. I'm sorry, it's in W1. So this is in A. Therefore, A is a subspace. Hope that's helpful.